Hi, my name is Bruce and this video is about multi-axis milling done on a manual milling machine. I want to make an impeller, a compressor impeller that looks kind of like this. This is for a model gas turbine. This is just a prototype, it's all messed up and there's lots of experiments and mess ups, but this is what I want to do. And the way that I'm going to do it is on my manual milling machine, and I know that CNC would be the way to do it, but I don't have CNC, I'm just a home hobby shop, and I know that CNC is kind of within reach of home hobby shops these days, but I kind of like the idea of doing it in a kind of nuts and bolts way. The work needs to be rotated in kind of two axes at the same time. So this is the fixture that I built to do that. Here's a new impeller blank. I put a mark on the OD just here, and you can see that as the whole fixture turns, the impeller also turns at the same time. So now the marker's over here, it started off at this corner. And that gives you the sort of double curve that I need. Here is the fixture in action. You can kind of see the two axes of rotation at once. It's Klein milling for by far better surface finish than conventional. The rough finish, I know it's a terrible finish. I'll talk about that later. The cutter is a 4-flute carbide cutter. I tried a 2-flute high-speed steel cutter and broke a bunch of them because they're just too flexible and they grab on sharp corners. There's an air blast to try and keep the chips down and try and keep them from getting pulled back into the cutter. I had the sort of concept of the shape in my head, but I couldn't figure out whether it would work, and I'm not good at CAD, so I made a modeling clay model, and it's just a plywood substrate with one of the curves on it, and then I put some clay on there and used a needle to kind of simulate the other curve as the axis, as the two axes turned, and then it kind of gave me roughly the shape that I was looking for, so I felt that that concept was good. Then I made a plastic version just for ease of machining, and that also seemed to be going in the right direction. Another thing I did is I made a plywood mock-up this is when it was on the lathe, being done on the lathe, to see if everything would fit. You know, everything has to fit under this chuck, and you have to have enough range of movement in all the axes, and there's a lot of moving parts, no pun intended. And so I did a plywood mock-up, and I think that was pretty worthwhile. Didn't take long, didn't cost anything, and certainly made the fixture work first time pretty much. So then I made the first aluminum one. This one was done on the lathe. The original concept was for the lathe, so the fixture goes on the lathe, and then and you're short of one axis. The way I configured it was a bit silly because I wasted one axis, and I was using shims to get the axis that produces the thickness of the vanes. That's why these ones look kind of thick. But you could configure it on the lathe to utilize the two axes that are available, the cross slide and the carriage, as well as the two rotational axes on the fixture. So that was very encouraging, and done on the lathe. This is the original setup on the lathe. I did not have a milling machine at the time. So it's just, you lose one axis, the third axis that you get on the milling machine. So the idea here is that you shim vertically to get the vein thickness. And then, as it happened, I managed to get a milling machine, a vertical milling machine, and this is the second one done on the vertical milling machine. And there I had a lot better success with having access to 3 linear axes. I had more success with controlling the thickness of the veins. A lot of experiments here, a lot of things wrong, but I was able to control the thickness of the veins a lot better. A lot of mistakes, a lot of learning. But that was the Mark II. At the bottom of the fixture there's just a base plate for mounting to the milling machine or the lathe. On the base plate runs a gear. This is just a change gear from my lathe on a stub shaft, and there's a lock to stop the gear from turning. Then there's a pinion which meshes with that main gear and runs around in a sort of planetary motion. And just a note on keyways, all of these keys and keyways are essentially light interference fits. Originally they were sort of normal key fits, but there was a lot of backlash in the whole setup, so I remade them all, and now they have to be pushed on, and hopefully much less backlash. Then there is a table which turns on the same stub shaft as the main gear below it, and the table carries this shaft which is for mounting the impeller. So the impeller will go on this shaft here like so, and there's a worm gear to drive the impeller which needs to rotate, and the rest is just pieces of plate bolted to the table to provide a framework for the shaft. The impeller shaft runs in ball bearings, ball races, deeper groove ball bearings, mounted in these plates in a countersink, a counter bore, and then so this bearing cannot move this way because of the counter bore, this bearing cannot move that way because of the counter bore. The shaft has a shoulder on it which goes between the bearings, and then this plate is the same as the right length, such that the shaft is then clamped, if you will, or at least restrained between the bearings so that it cannot move axially. There's no axial play, because you're machining the impeller and you cannot have any movement other than the movement that you want. So that's how the axial restraint is done. So now with the table and impeller shaft mounted on the base plate, you can see that it rotates around the stub shaft, giving you one of the axes of movement, and as the pinion gear rotates, as it follows its planetary motion around the main gear, it turns this shaft. You can see the shaft turning if you look carefully. And in fact, this shaft is the input shaft, so this shaft is driven, which drives the whole table in this motion and gives you one of the axes that's required. Then a worm goes on the drive shaft and drives the worm gear, so that as the table rotates around the stub shaft, the drive shaft turns, the worm turns and drives the worm gear, which drives the impeller shaft. So now you've got two axes going on at once in the correct ratio. So the pinion gear is sized with respect to the main gear, and the worm to the worm gear to give the right ratio for the correct amount of turns per turn, if I can say that. The ratio of turns on this axis compared to this axis is what I want. In fact, this worm is a 3-start worm. You can probably see the 3 starts on the top of the worm, and I think it's 22 teeth on the 21 or 22 teeth on the gear, so that's like a 7-to-1 ratio here in the worm set, and then a 4-to-1 ratio on the pinion and main gear. The bearing plates of the drive shaft have oversized slotted whatever holes and plate washers so that the center line of the shaft can move around in order to adjust the gear mesh. But there's 2 gear meshes involved. There's the pinion and the main gear, and that needs to be adjusted on a line between the centers here. And then there's the worm and the worm gear, which is on a line like this. So you've got 2 different meshes to adjust. So this shaft has to move around to get both meshes adjusted. That also means that the worm gear has to move back and forth on the shaft in order to adjust the mesh, because this input shaft will move on a kind of a curve rotating around this point, and so it'll move back and forth this way for this mesh. So that's why these nuts here and spacers to adjust the worm gear to line up the mesh and then stop thrusting. Now there's one other function that the fixture needs to do, and that is to index. So clearly there are multiple vanes on the impeller, and 14 in fact, and so I need to index 14 times. So how to do that? Well, same setup, except that the lock is off the main gear and there's a table lock on. So this is just a post screwed on to stop the table from rotating. That now the table can't move, can't rotate, but the main gear can. So when you turn the drive shaft, the impeller shaft turns and the main gear turns, and you can index to the next vane. And then there's just a little detent here to index to. And one other feature is this pin here, which is mounted, it's actually glued in to the stub shaft, and the idea of that is it's a datum point. So it is a known distance from the axis of the impeller shaft in all 3 dimensions. So then you can touch off on this datum pin with the cutter in 1, 2, 3 directions, and then you can have a datum. You can take the fixture off the milling machine, put it back, recover the datum, and so on. You may also have noticed these circular marks here, these kind of gramophoning marks. Again, these plates were faced on the lathe, and I didn't know it at the time, but the lead screw, the cross slide lead screw, was bent. Somebody had crashed the lathe at some point and bent the lead screw, and with the gibs not tight as they should be, it gave this pattern when facing, and this corresponds to the lead screw pitch, this annular sort of tree rings. So there you go. Figured it out eventually, straightened the lead screw and back in business, but in the meantime I'm not going to go back and remake all of these. So, circles of chagrin. So there's the finished fixture. It's mounted on an angle plate because I need this axis here and this axis here to be perpendicular to the cutter, the milling cutter axis. And here it is set up on the milling machine, and you can see the kind of the motion now. I have an air nozzle here blowing on the cutter to clear the chips. I found that it's really important to clear the chips with such a small cutter, because if you don't, and also if chips are not evacuated with a soft gummy material like this aluminum, the chips get pulled around and into the cutter and welded onto the surface of a slot, and that gives a terrible surface finish, and it also, I don't know what it does to the loads on the cutter, but it can't be good. Here's an example: conventional milling with an air blast, and just look at how the chips are packing up on the cut side of the cutter there. Only problem with the air to evacuate chips, it blows them everywhere. Absolutely everywhere. I don't have a DRO on this machine, so I'm using an ARO right here, analog readout. I'm using the scale readout on the table plus the 0 on the dial of the X travel plus a dial gauge to control my X movement. The dial gauge to get it accurate, and this is necessary because you can easily be one turn out on the dial gauge, so it's really important to keep track with the basics. Also, I've been using stops, so I set the stop just behind the desired dimension, so that again, if you're one turn out on the dial gauge, you can know where you are and keep under control. So yeah, DRO for sure one day, for today not there, so dials. There's the finished impeller before deburring. It's much better than the Mark 1 and the Mark 2. Dimensions are much more under control. Surface finish is, yeah, on here, on this one it's finally getting to be where I would like it to be. And of course I messed up. If you look here, one turn too many on the depth on the Z, and I didn't notice. I was excited, it was the second to last cut, and I messed it up and ruined the part. However, this is still a prototype, so it's for learning. Beer is for consolation, mistakes are for learning. There's the Mark III impeller after a bit of deburring. It's not bad, it's coming along, it's much better than the Mark II or the Mark I. Still some mistakes. Rushing at the end. I went one turn too many on the Z and took out the back plate. You can see here where it's kind of squared off in that corner. I've run too far with the milling cutter on the center line of the splitter vane when it's indexed to the splitter vane, and it's moved over too much to bite into the main vane. But overall, it's actually not beginning to look too bad. So that's it. Manual multi-axis milling. A lot of fun and amazing what you can do with a basic machine and principles. Hope you've enjoyed this video and learned or been inspired, laughed a bit maybe. Bye for now.